Welcome, everybody. I'm very happy today to introduce Herbert Edelsbrunner, who is going to talk about expected length of EMST and expected one norm of chromatic persistent diagrams.
Thank you very much, Henry and Barbara, for the invitation and for running this seminar. I'm going to talk about something that I worked on with Ondra Dragunov, Sophie Rosenmeier, and Morteza Sagafian during maybe the last 2 years. Well, it depends on the second part, longer than that, maybe 3 or 4 years. The talk is really of two pieces. The first one is about the length of the Euclidean minimum spanning tree, somehow connecting to classical results in probability theory. And the second part about the chromatic persistence connects the classic part of probability theory to topological data analysis and stochastic geometry. All right. So let me just jump into the 2 results. So 2 topics, 2 results. First result is a theorem. If you have n points uniformly distributed in the unit square, independently chosen, then the expected length of the minimum spanning tree, Euclidean minimum spanning tree, is in the limit some constant times square root of n. Perhaps this should not be surprising, because when you have 4 times as many points, the edges shrink by a factor of 2, and so the whole thing grows with the square root of n, not with linear. So the square root of n should be clear. The constant c also seems to be at least plausible, but it turns out it's a difficult problem. So the constant c is known to exist, but we do not know what it is. And I want to shed more light on this constant c. So this is called the asymptotic constant because it exists when n goes to infinity, the number of points. All right, so that's the first result. That's a classical result in probability theory. And the second one is we looked at the 6 persistence diagrams in chromatic persistence: kernel, relative, co-kernel, domain, image, and codomain, and found that when we take 1 norms, we also get asymptotic constants. And these asymptotic constants are indeed related to the asymptotic constant of the minimum spanning tree. If you read the formulas, the asymptotic constant is always a function, and there happens to be a c sometimes, and sometimes a c sub l. And c sub l is another asymptotic constant of a different type of minimum spanning tree, which I will get to perhaps at the very end. It's kind of a new geometric structure or stochastic structure that came out of this research. I will not talk about it much, if at all, but I believe that Ondra will give a talk soon in this format and talk more about this, of what we call a lunar minimum spanning tree. All right, so these are the 2 results, and I want to rationalize the whole thing. First of all, everything I talk about is in a plane. Here is a set of points in a plane, and what you see is the Delaunay triangulation. And I distinguish 3 types of edges: dotted, dashed, and solid. And the meaning of them is the solid edges are the minimum spanning tree, which is known to be part of the Delaunay triangulation, or Delaunay mosaic, as I call it, for decades. The solid and the dashed edges are the Gabriel graph. This is the graph that you get by connecting 2 points. Whenever the circle centered at the midpoint of the edge, passing through the 2 points, is empty of other points. Okay, so it's also a subset of the Delaunay triangulation, and you see the dashed ones. And the dotted ones are the remaining edges of the Delaunay triangulation. In the language of the radius function on the Delaunay triangulation, perhaps you are familiar with that. A radius function is, for it defines what an alpha complex is when we grow disks from the points when a particular simplex comes into the alpha shape. And this radius function, when you look at the edges, distinguishes between critical edges and non-critical edges. And the critical edges are exactly the dashed ones and the solid ones. And the difference between the solid and the dashed is that the solid are death-giving in the language of persistence. The dashed edges are birth-giving in the language of persistence. Okay, so really everything I talk about is this distinction between birth and death of giving for critical edges in a Delaunay mosaic. And I only talk about 2 dimensions. Higher dimensions is more complicated. All right, let's start with a little bit of Delaunay mosaics in a random case, in particular Poisson point process. I call this a Poisson-Delaunay mosaic. And for us, interesting is if you have a Poisson point process, how many edges are critical in expectation? Okay, in short, if you're not familiar with the Poisson point process, it's like a uniform distribution, except it's not in a finite domain, but it could, for example, be in the entire plane. So everywhere in the plane, we pick points so that we get an infinite set of points. In every region, there's a certain probability that you pick a point or several, and this is called the Poisson point process. Also, what's interesting about it is if you take a point process in the plane, but then you take the subset of points inside of the unit square, this is a uniform distribution. Except that if the intensity of the process is n, then the number of points in the unit square is in expectation n, and could be something different. Could be n minus 1, n minus 2, n plus 1, etc. The reason why I talk about point processes instead of uniform distribution is because in a Poisson point process, it's everywhere in the plane, so I don't have to worry about boundary effects. And this is very useful for computations. Okay, so how many critical edges are there in expectation? So this is encoded in this little matrix here. 1, 1, this is the number of critical edges, and it says 2 here. To understand that is, if you have n points, we get 3n edges in the mosaic, Delaunay mosaic, and 2n of them in expectation are critical. So 2/3. It's a very clean result. It has been known to Roger Miles in 1970 or so, but we will need a little bit more information in order to prove what we want to prove. Maybe I also remark the 1 here that's circled. This is the matrix entry 2 and 2. This is the critical triangles, number of critical triangles. The Delaunay triangulation, Delaunay mosaic has about 2n triangles for n points, and half of them are critical. Critical triangle, I remind you, is one with all angles smaller than pi/2. So it's an acute triangle. Okay, I said I need a little bit more than just to know how many critical edges and critical triangles there are. So in order to explain that, I need gamma functions. I'm sure you know the complete gamma functions, which are written with an uppercase gamma. There's also something called the incomplete. There's a p missing. Incomplete gamma function, little gamma, has 2 parameters, k and x, and it's this integral for t to 0 to x of whatever it is. So this is called the incomplete gamma function. The complete gamma function is when the x goes to infinity, or when it is infinity. And you probably remember the complete gamma function of an integer k is k minus 1 factorial. But the good thing about it is also defined for real numbers between the integers. And the ones that I will need today is gamma of 1/2 is square root of pi, gamma of 3/2 is half of square root of pi, and gamma of 5/2 is 3/4 of square root of pi. You can look this up in Wikipedia, for example. I felt uneasy about gamma functions for a long time, but then Anton Nikitenko, who I worked with for some years, he said they are really cool once you get to know them. And so I made an effort. All right, so here's a theorem that I need, proved in a paper with Anton Nikitenko and Matthias Reitzner, 2017, namely that in a Delaunay mosaic, we know the number of critical or expected number of critical edges, but we know it for every threshold of radius, for R0. So this means I'm going to take the alpha complex for the threshold R0, and then I know that in expectation, the number of critical edges is 2n times the value of the little gamma function from one, so this is for edges, and x is n times pi times R0 square. Okay, and then in the graph here, you see the gamma function. So 1, 1, this is for critical edges. And for 2, 2, this is for the critical triangles. So they start later and end earlier. And 1, 2 would be the edge triangle pairs, which are not critical. And it turns out that it has the same expectations as the critical edges. All right. I need a corollary of this thing, which says I can also figure out the expected length of all the edges, critical edges, of radius up to R0. And it's not too difficult to see why that is possible, because I know how many edges, critical edges, there are of a certain length, so I can just integrate. Anyway, so this is the number. Perhaps you remember little gamma of 3 over 2, sorry, the complete gamma function of 3 over 2 was 1/2 square root of pi. So square root of pi cancels with this pi over here. The 1/2 cancels with the 4 under the square root. So the expected number is square root of n, meaning the expected length of all the critical edges is square root of n. And expected sum of triangles of expected sum of radii of all the critical triangles up to radius R0 is this expression. And it turns out the triangles play a big role. So maybe I figure out how much this is. Complete gamma function of 5 over 2 was 3/4 square root of pi. So the square root of pi again cancels. And so this expectation is 3/4 square root of n, the expected sum of radii. So there's half as many critical triangles as edges, but their expected sum of radii is 3.5 or 3/4 times as much as those of the edges. Something we might want to remember. Okay, so I'll get to a proof of the expected, a proof of the result, which is a lower bound. Okay, let's get to this. So first, a little bit of background, historical background about this asymptotic constant that I mentioned, which is the expected length of the minimum spanning tree is c times square root of n. So that's the theorem. That this constant c exists was proved in 1959 by Beardwood, Halton, and Hammersley. That was a very influential paper. There were lots of follow-up work in stochastic geometry after that. In particular, Michael Steele worked on this in extending it, and other people. But to my surprise, when I learned about this, the constant c was known to exist, but until today, we don't know what it is. We have upper bounds and lower bounds. So the best upper bound is pretty old also, 1965 by Gilbert, is at most 0.7 something. And the best lower bound, 92 by Afram and Bertzimas, 0.6 or something. And the new theorem I wanted to mention is, or to talk about is, we improved the lower bound to 0.62. Seems like a minor result, but it's a really cool thing, I think. And I cannot go through the proof, although it's not too long, but I want to get the proof idea across. By the way, I wanted to mention that these graphs, or these gamma functions, these are from a paper that Anton Nikitenko, Kati Ölsberg, and Peter Sinak did in 2020. And what's interesting about this is this, in this picture, I split up, let's see, the edges. The edges with a disk, those are the death-giving, and the edges with an empty circle, those are the birth-giving. Okay, so those are not gamma functions anymore. And indeed, those are just experimental results. We don't know how these birth-giving and death-giving things split up probabilistically. And indeed, I think that's the core difficulty in a minimum spanning tree, that whether an edge is critical is a local property. Just figure out whether the circle centered at the midpoint is empty. The distinction between a birth-giving and a death-giving edge is global. It's a topological distinction. So it's much more difficult probabilistically. And actually, we don't really know much about it other than this experimental result here. Okay, getting to the proof idea. So here's a simple idea which doesn't work. Namely, how about I choose R0 such that I expect n edges? And those would be the n shortest edges. And then I take their length, which is this expectation. And then I say, well, the n shortest edges, assuming I have n plus 1 points, the n shortest edges in total are not longer than a minimum spanning tree, which consists of n edges. Okay. So this is true. But the problem with this is that when I look at the expected length of the n edges, it's 0.29 times square root of n. Sorry, this is the radii, the sum of radii. So I always have to multiply with 2 in order to get the length, because the length of an edge is twice the radius. Okay, so this would be a lower bound of 0.58 times square root of n, which does not beat the best lower bound by Afrim and Bertsimas. That's why I said it doesn't work. So we need to be a little bit more sophisticated, and that's what I want to do next. Namely, I increase the radius R0 a little bit, such that I expect a number of critical edges minus number of critical triangles to be n. And the reasoning is that if there is a birth-giving edge that's short, then this is paired up with a critical triangle. Because birth-giving edges and death-giving triangles are always paired by persistence. The radius of the edge is smaller than a triangle because the triangle comes later. So if I have a lot of critical triangles, this means I also have to have a lot of birth-giving critical edges, and the birth-giving critical edges cannot participate in the minimum spanning tree by definition. Okay, so if I can show that there are lots of them, then I have to be more tolerant with the length cutoff for the minimum spanning tree. And indeed, I can go up to 1 over square root of n times pi. And also, if I do this, then the expected sum radii of the edges minus the radii of the critical triangles is 0.31 times square root of n. Okay, so it's a little bit higher. I know that the birth-giving critical edges can only be shorter than critical triangles. So I'm on the right side of this. And then if I double it, because I want to go to the length, I get 0.62 times square root of n. And that's the new lower bound for the asymptotic constant.
Herbert, can I ask a question? So you have this new lower bound of 0.62. I think there was an older upper bound of 0.7 or so.
Yes.
What do simulations show should be like approximately the value of C? Do you know?
I'll talk about this.
Oh, perfect.
Yeah. Hold on for 20 minutes. I don't want to say much more about the proof other than the difficulty, mostly a technical difficulty, is that the Poisson point process and the uniform distribution are not the same. The Poisson point process allows me to ignore boundary effects, but then near the boundary of the unit square, I get different edges from the uniform distribution. And mostly it's about showing that not too many edges are different. And also the total length of those edges is very small, namely a constant. Okay, I don't want to say more about it. And get to the second topic, which is chromatic persistence. First, a brief introduction, although I think since you're at this seminar, you probably know persistent homology, so I don't have to say too much. Here is a picture that maybe you've seen before, a point set, growing disks, the dual alpha shape that slowly becomes the Delaunay mosaic. And the reason why we like alpha shapes, or I like alpha shapes, is because the homotopy type of the alpha shape is the same as a union of disks. And so when I do a topological analysis, I can use the alpha shapes instead of the union of disks. So it's computationally much easier. So we do this persistent homology. We get the persistent module for each dimension, and then we get a barcode. And each bar in this barcode means there's a, so I think in this case, it's a one-dimensional barcode, which means it talks about cycles. So here is a long bar, means at the left end point, a cycle was born, and at the right end, it dies. And I think this is this small little cycle that you already see in the first figure, and it's filled up in the second figure already. And then later, there's another cycle born, which is this big area. Even in the second one, it's not a cycle yet. In the third one, it's a cycle. In the fourth one, it's filled. Okay, so this is persistent homology. But we want to do this for color data, meaning at least two different colors. So here, my examples today will all be just two colors, blue and orange. And you could ask, like here's a blue point set, how does it interact with the orange points? And in particular, you might see some three blue cycles partially filled by orange. This one is not filled at all by orange. And somehow we want to figure out the difference. And then I say more about the connection to minimum spanning trees. So you can look at different barcodes. And the one that talks about filling the blue cycles with orange points is the kernel. So this would be, we would take the kernel of the Delaunay triangulation of the blue into the Delaunay triangulation of the blue and orange. Take the kernel and then take the persistence of that. And then there you get two bars. And the interpretation of the two bars is this circle enters the kernel pretty early on because the orange fills it up. And much later, the circle dies because the blue itself fills it up if the radius is big enough. There's another short bar, which is, I think, this cycle, partially filled by orange. And this cycle is not filled by orange at all, so it doesn't show up in the kernel at all, but it shows up in the blue. So blue had three cycles. All right. The prior work on this is Cohen-Steiner and other people worked on image kernel, co-kernel persistence in 2009. So this is instrumental for this construction. And then Coultrera and co-authors in 2025, or actually the years before that, developed is a chromatic persistence diagram for it, based on image kernel, co-kernel persistence, etc. Okay, long story short.
Herbert, there is a
Yeah.
question. So someone is asking you to please repeat what is the kernel here exactly. So of what things have we taken the kernel here?
Yeah. So at a particular radius, you would take the alpha shape of the blue, and then you also take the alpha shape of the blue and orange together. Maybe I should not go to the alpha shape, but rather to the union of disks, because the union of blue disks is obviously contained in the union of blue and orange disks. Okay, so this is an inclusion. And the kernel is, so if there's a cycle in the blue, which is not a cycle in the blue and orange, then it's in a kernel.
Mm-hmm.
Yeah. So typically it starts when there was a blue cycle, but somehow it fills up by orange. And it dies because the blue cycle disappears because the blue points themselves fill it up, which eventually happens.
So is it correct to say that that would be the kernel of the persistent homology of the blue disk into the persistent homology of the blue plus orange disk?
Yeah.
Okay.
Although the way we formalize it is we take the kernel and then we take the sequence of kernels, and then that gives persistence module by themselves.
Mm-hmm, mm-hmm.
Right.
All good.
Yeah, and we do 6 different views of things that somehow display different topological interconnections, and call this a 6-pack. And the kernel is only one of them. The image is another one. The co-kernel is here. The domain, which in the example before was the blue, or here it's also the blue. The codomain is the blue plus orange. And the relative diagram is the most interesting, but maybe also most mysterious one. So for today, I will blend it out and use the real estate to explain something else. So here, just some examples to get you a little bit more comfortable with this 6-pack. Here you see the 3 blue cycles. So if you ignore the orange, and these 3 blue cycles are 3 points in the domain, because the domain is the blue. 2 of the blue cycles are filled, at least partially, by the orange. That's why they show up in the kernel. So these are the 2 bars that we saw earlier, now in the persistence diagram, points away from the diagonal. In the image, so here are blue cycles which are in the image, and they are in the image before they end up in the kernel. So this blue cycle stays in the image all the time, because it's a blue cycle that's also a cycle in the blue and orange. This cycle is only partially filled by orange, so it stays in the image for a while before it migrates to the kernel. Okay, so there is indeed, so this is this point down here, there's a connection to the kernel. So when this guy dies, it wakes up here. So I think it's this point. You can go here, reflect it on the diagonal, go up, end up at this point. So there's some interaction between the 6 persistence diagrams in the chromatic persistent homology. We formalize this a little bit because it's useful. And so there we have 3 relations, 3 short exact sequences that some are encoded here. And maybe the one that's easiest to understand is the kernel into the domain, into the image. So here are the short exact sequences. It's a standard topic in algebraic topology. If you're not familiar with it, it takes a while to get used to it, but it's a very handy, very compact way of writing a lot of very rich information. And there's another one from the image to the co-kernel, and another one from the co-kernel to the kernel. The last one is, in fact, kind of interesting, because you see, the index P is always the same. That's a dimension we're talking about. But when you go from the co-kernel to the relative diagram to the kernel, the index drops. So this is something also typical in homology, that you always run in circles, but actually once you complete a circle, you're in a different layer. So you really walk in spirals. All right, there's consequences of those exact sequences, namely the one norms. So the one norm of a diagram, I mean the sum of persistences of the points in a diagram. So the one norms of particular diagrams add up to the one norm of another diagram. For example, the kernel and the image add up to the one norm of the domain diagram. Okay, and this will be useful. In fact, it will, let's see, is this used in our proof? No, I forgot. Ignore the last second. All right, so now I'm getting to the expected one norms. I want to switch to a different chromatic model. Namely, I used to say blue maps into blue and orange. It's a little bit nicer if you take the blue and the orange separately and map them into the union. So this is like taking the blue union of disks, the orange union of disks, and then map them into all of the disks. So this is in drawing here. The blue maps down to the middle, the orange maps up to the middle. So this is symmetric between blue and orange, and therefore somehow mathematically nicer. And for the rest of the talk, I use this idea. And I call the blue disjoint orange the monochromatic diagrams, and the union the bichromatic diagrams. Okay, so I get to this table that I showed you earlier. There's various relationships. The one that's fairly obvious is that the codiagram C0, the constant so this is the constant such that the one norm is this constant times square root of n in the limit when n goes to infinity for a random set of points in the unit square, is half the asymptotic constant for the minimum spanning tree. But this, I think you should know, or it should be natural to you, because the norm is keeping track of radii, birth and death. And when we look at dimension 0, we really talk about connected components. And so a death happens when two disks meet and two components get merged. This happens at a radius which is half the length of the edge. And this edge belongs to the minimum spanning tree. So this is one way you can think of constructing a minimum spanning tree. Growing disks, when two disks meet, figure out whether it's two different components. If yes, draw the edge. Okay, so this relation is obvious. The one that's less obvious is the next one. The one-dimensional. So how does the minimum spanning tree relate to one dimensions? And this is because, let's see, I forgot how this works. The constant, asymptotic constant for the one dimension is half c minus 1/4, because the expected sum of radii of the critical triangles is 3/4 square root of n. This is 1 times square root of n, so here we have the minus 1/4, plus half the length of the EMST, so that's c half. So that this gives the answer. But why is this the case? Oh, because when I look at the one-dimensional persistence diagram, the deaths happen when the critical triangles appear. The birth happens when I look at the critical edges that are birth-giving. But I don't know which ones are birth-giving or death-giving, so I take all of them, and then I compensate by adding back the death-giving ones, and those are from the minimum spanning tree. Okay, so this way I connect the zero-dimensional and the one-dimensional persistence diagrams. And then here you see the various things that follow from that. So each entry here is a dimension of one of the diagrams in a six-pack. And there's a constant, and there's a C sub L, which I maybe get to at the end of the talk. But before that, I'd like to say a little bit about these constants. And I draw them. So here on the horizontal axis, I have the asymptotic constant for the minimum spanning tree. And we know it's between 0.62 and 0.7 somewhere. And I show the values of some of the constants, 6 of them. And we see they're nicely ordered. This is a particularly interesting point because so these are two constants that somehow meet right where Gilbert proved the upper bound for the asymptotic constant. We still don't know whether this is a coincidence or it's a hint of maybe proving Gilbert's result in different ways. Namely, maybe the kernel is always at least the domain. Zero-dimensional kernel is always at least a one-dimensional domain measured in one norms. In expectation, in general, it's not true, but maybe in a random case, it's true. All right, so I wanted to point this out. And the other thing is that it's natural that the one norm of a persistence diagram cannot be negative. It's always positive, but this already constrains things. So this is actually a powerful insight that gives bounds on mathematical concepts. And in particular, we were able to prove, so we get an inequality from a relationship for this constant that relates C and CL. CL is this new lunar minimum spanning tree. And we get another relationship. And so now we also know that the constant for CL, which we don't know anything about, we proved recently it exists. But this already gives it's between 0.26 and 0.5, just by looking at the relationships between the diagrams and the ones that are implied by the short exact sequences. All right. Coming to Henry's question, we did experiments where we computed the one norms of all the diagrams in a six-pack, and you see two curves. So from left to right, the number of points increases. The curve itself shows the constant times square root of n. So this has the square root of n behavior. And there are two of them because we show it for the square and also for the torus, just to see. And for the torus, there's a little bit more opportunity to connect the minimum spanning tree because you can go around. So the torus minimum spanning tree should be a little smaller. And indeed here, and then from these curves, we then estimate the constant. So that speaks directly to Henry's question. And so we get 0.35. So the constant here would be then, oh, this is CL. I don't want to talk about CL yet, sorry. Yeah, here we have a few more of these diagrams. Here's an estimate of C, 0.64. Okay, 0.648. This is roughly what our experiments show. I think between 0.648 and 0.649, everything happens. It is interesting because in the literature, we saw only 3 other papers that did experiments to estimate the constant. The reason why there's not more work on it is this converges very slowly. So it's a real pain to do these experiments. But in any case, our results are between the lowest estimates and the 2 highest estimates. And we have a lot of different angles at it, so I trust a little bit more of what we show here than what's in the literature. Okay, I come to the end of my talk. So here is the lunar Euclidean minimum spanning tree. And just explain what it is, not say anything more about it. So here we have 2 colors. the points, the colors are the solid points and the dotted points. And we look at loons. So I always take a solid and a dotted point and I intersect to do disks. So this gives what we call a loon. So here's a loon. And the persistence game is played by growing the disks, and therefore the loons grow. I forget about the disks. I just keep track of the union of the loons. And the union of the loons play the same game as earlier for the disks. They merge sometimes, so there's critical edges and critical triangles and birth-giving and death-giving. And the minimum spanning tree is now, for example, here there's a point. This is the point that corresponds to the loon between this solid point and this dotted point. It wakes up at a certain moment, namely when the two disks meet. So now the vertices of the minimum spanning tree also have costs, the time when they start to exist. And the edge is when merging happens. And then the cost of the whole tree is the sum of the edge costs minus the sum of the vertex costs. Conveniently, again, plus the minimum vertex cost so that it's exactly the one norm of the persistence diagram. And I think Ondra is talking about this. So I promise what Ondra has to deliver. Very powerful position I'm here. And with that, I thank you for listening.
Thank you very much. I will ask now everybody to unmute themselves and clap to the speaker. Any question? You can raise your hands or unmute yourself if there aren't too many, or you can ask them in the chat, of course. Let me see if I can see any raised hand.
I'll ask a question. So I don't know if I should ask this question for one-dimensional homology in the plane or for, arbitrary dimensional homology in higher dimensions, but I'll try for higher dimensions. So like, let's say we're in d-dimensional space. I think the square root of n for the lengths of the minimal spanning tree now becomes, instead of to the power 1/2, it's n to the power d minus 1 over d, I think. And then you could ask the constant in front for the minimal spanning tree. I'm curious what's known about that, if anything. And then you could also ask if it's been proven if there's a constant that exists for I-dimensional homology in D-dimensional space. Do you know, have folks proven that a constant exists there?
So higher dimensional minimum spanning trees, the constant exists. So there is work. What it is, I think the trivial approach that I started that didn't quite work out, I think that might work. Just look at this n smallest, shortest edges. The more sophisticated approach where I take care of I use the triangles already stops working in 3 dimensions. Because, well, unfortunately, in 3 dimensions, I have birth-giving and death-giving triangles. And so I don't know anymore which ones to use and then how they interact with the tetrahedron. Maybe there's something there, but we didn't know, or we don't know. Let's see. So this is about the 0 dimensions in higher dimensions. If you go higher homology degree, not much is known. So I think people, first of all, didn't look at this because I think our paper is the first one that somehow draws the connection between persistence diagrams and minimum spanning trees in this whole stochastic analysis of the asymptotic constant. The only thing that's known is this lunar tree. So for the lunar tree, we proved that the asymptotic constant exists in a plane, only in 2 dimensions. And its cost is the one norm of the relative diagram. So there's a relationship between the relative diagram and the lunar, which is not direct, and I skipped over it. But we also proved that the asymptotic constant exists for more colors than 2. And so then this relates to the relative diagrams of degree d minus 1, I believe. But to my knowledge, that's all we know in this direction. I think the higher degree, and also 3 dimensions, also higher dimensions, is very interesting. It's a rich playing field, so lots of interesting things could happen there. And I like the stochastic geometry connection, because somehow just to know that half of the triangles in the Delaunay mosaic are acute and the other half is obtuse. Yeah, it's a cute fact, and I think very few people know about it.
Thank you.
We had another question in the chat that is, if you can talk again about what is the Lunar EMST, but then Ondra arrived an answer in the chat. Yeah, but maybe you can still say something aloud about the definition of it, even if Ondra already answered.
Okay, so I have 2 colors of points, solid and dotted. Grow a disk around each point, but only consider the intersections of a solid disk with a dotted disk. So this is a loon. And then as you increase the radius, the loons grow and they form components. Now a component also wakes up at a certain moment, it merges with other components. So whenever a loon wakes up, there's a vertex. Whenever 2 components in a union of loons meet, there's an edge. And this defines the lunar EMST. And then the cost is always the radius when the event happens. And we take the edge costs minus the vertex costs.
Okay, thank you. I'm not seeing any other raise hand or question in the chat, so maybe, oh yeah, sorry.
Can I ask a follow-up question about the lunar EMST? So you touched a little bit on some statistics of C sub L, so this constant related to the lunar one. So
Yeah.
was that when both the dotted and the hollow point, or the solid and the hollow points, were sampled Poisson processes with the same intensity? And have you considered all different intensities for the 2 classes?
We did. So the experimental results are for a range of different densities. I forget now what the results were. Maybe Sophie can talk about this at some point. Then eventually we simplified everything and we just talk about the equal probability. Yeah. A useful result in this context is if you have a Poisson point process of intensity n, and you randomly color every point with one of 2 colors, then each color is a Poisson point process with intensity n over 2. So Poisson point processes have all these nice symmetry properties that are convenient when you want to prove mathematical results.
Thanks.
Okay, we still have time for questions, but maybe I will stop the recording and then people can ask questions that will not be posted on YouTube.